halogens, chlorine and bromine, add to alkynes, and we get a vinyl dihalide, and they may add in a syn or anti, so the product is a mixture of cis and trans isomers, and it's difficult to stop the reaction at the dihalide, so we normally end up with 4 halogens stuck on there. 2 moles of halogen can add to the triple bond, getting a tetrahalide. So this is very analogous to what you learned in the alkene chapter. Here's a carbon with a hydrogen. Here's a carbon with none. This adds across the triple bond. The rich got richer. The poor didn't get anything. Well, they got the halide. So we see that this is very analogous to what goes on with our alkenes. We get Markovnikov regioselectivity. And once again, we can add 2 moles of the hydrogen halide, producing a geminal dihalide like we see here. So here's 1 pentyne, giving us 2 bromopentene, which is the Markovnikov product. And we see that we get both E and Z isomers. Now notice here, there's no hydrogen, so we get equal amounts. It's a toss-up. Who gets the hydrogen, who gets the bromine? So no Markovnikov regioselectivity because each of these carbons are equivalent. Similar mechanism, electron-rich region grabs the proton. Remember, this bond's polarized, partial negative charge, partial positive. Electrons jump on the halide. A vinyl cation is produced that hits there, and here's our Markovnikov regioselectivity. We say the triple bond extracts a proton from the hydrogen halide, forming a vinyl cation, and the proton adds to the least substituted carbon, forming a vinyl cation. So just like with the alkenes, if we run HBr in the presence of peroxides, it goes by the free radical mechanism. Involves a bromine radical. The bromine radical is going to add here to make the more stable radical, which is going to be the more highly substituted. And so we get anti-Markovnikov regioselectivity. And so the poor here got richer, and we get both E and Z isomers. Hydration of an alkyne, mercury sulfate in aqueous sulfuric acid, adds water across one of the pi bonds, and we see Markovnikov orientation, forming a vinyl alcohol. We call it enol. The enol rearranges to a ketone. Hydroboration, oxidation, adds OH with anti-Markovnikov orientation and rearranges to aldehyde. So very similar to what we saw with alkenes. So here's our mercury sulfate and sulfuric acid, and this hydration is catalyzed by the mercuric ion, and the addition makes this vinyl alcohol, which we call an enol, and it rearranges. We call that tautomerization, or we say this quickly tautomerizes into this ketone. Almost looks like this hydrogen comes off and goes there. Turns out it's a different hydrogen. So here's a quick mechanism. Double bonds grab this mercury. It goes to the carbon that already has a hydrogen to put the charge on the more substituted carbon. So here's our vinyl cation. Water then hits. Water deprotonates this thing. So here's an organomercurial alcohol. And then hydrolysis is going to take the mercury off. Double bond grabs the hydrogen. So here's a resonance stabilized intermediate. And under acidic reaction conditions, mercury is replaced by hydrogen to give a vinyl alcohol called the enol. So here we see an enol, and it tautomerizes into a ketone. Enols are not stable, and they isomerize to the corresponding aldehyde or ketone in a process known as keto-enol-tautomerism. What is the mechanism? So here's our vinyl alcohol, the enol form. Looks like typical alkene chemistry. Grabs that proton, puts a positive charge there. And you can draw these 2 resonance structures. These electrons jumping down, forming a double bond, putting the positive charge on carbon. then once you have that, water can abstract that proton, leaving you in the keto form. We say this is acid catalyzed, and we regenerated our catalyst. And you can see this hydrogen doesn't move over here. This hydrogen came from somewhere else. Came from right there. Hydroboration oxidation. So you'll recall in the alkene chapter we had BH3 and THF. Then we'd have hydrogen peroxide under base conditions. So here's our boron reagent, and it has this alky group, sec isoamyl, and there's two of those stuck to the boron atom. And this is going to give us anti-Markovnikov additional water across the triple bond. And this reagent we say is a hindered alky borane, and it's used to prevent two molecules of borane from adding to the triple bond. And this borane has two bulky groups. See, there's two of these stuck to a boron, and then boron likes to have three bonds. The third bond is to hydrogen. So there's the triple bond. This thing adds, so this hydrogen goes there, the boron compound goes there. And notice this is just like the last half of the BH3 and THF reagent. Hydrogen peroxide in the presence of base removes this and replaces it with an OH. So there's our enol, and it tautomerizes, and so here's where we get an aldehyde instead of a ketone. In the second step of the hydroboration oxidation, a basic solution of peroxide is added to the vinyl borane to oxidize the boron and replace it with a hydroxyl group. Once the enol is formed, it rapidly tautomerizes in base to the more stable aldehyde. And the base catalyzed tautomerism. It's a little easier to visualize than the acid. Here's our enol, our vinyl alcohol. Hydroxide comes by, pulls off this hydrogen. This thing is stabilized by resonance. These electrons jump down, forcing these to jump over there. Now we have a negative charge there. And this negative charge we see grabbing a proton off of water, creating a hydroxide, and giving us the aldehyde, the keto form. So once again, we say this is base catalyzed. A catalyst helps a reaction occur, but is not consumed. So it's always nice to see our catalyst regenerated. Oxidation of alkynes, very similar to what we've seen with the alkenes. So potassium permanganate, if we're dilute and neutral, it will oxidize an alkyne to a diketone. If we're warm and have basic conditions, the permanganate will cleave the triple bond. And finally, ozonolysis, followed by hydrolysis, cleaves the triple bonds. Very similar to what we've seen with the alkenes. So here's permanganate, water, neutral conditions, and we get 4 hydroxyl groups here. 2 waters can leave and give us the diketone. Call this a tetrahydroxy intermediate, and there's our diketone. So under neutral conditions and dilute, permanganate. Now if we use permanganate under basic conditions, or if the solution is heated too much, we oxidatively cleave this bond. We can imagine the tetrahydroxy. We can even imagine the diketone, and then chopping that off and getting under base conditions these conjugate bases of the corresponding carboxylic acid. Adding a proton, we get our carboxylic acids, in this case acetic acid and propanoic acid.